So good morning. So I think in the last class we were looking at RSA crypto system. I quickly reviewed it because I think you know about it anyway. The important aspect that I'm going to discuss now is how do you attack RSA crypto system, right? So as you know that the crypto system is based on integer factorization problem. If an integer n can be broken into because you require two large primes and you multiply them and you get n. So if you given n, if you can find out p and q, then you can break the system, right? So the question is, uh, how do you find this factorization, right? So there are certain techniques which people try to use, and one of the important and related problem is primality testing. So what do you mean by primality testing? So given an integer n, and you need to find an algorithm which can tell you whether it is a prime or not. Primality testing, right? So from the time of Gauss, this was a very interesting problem actually, and people were trying to find polynomial time complexity algorithm for primality testing, and since last, I mean, 350 or 400 years, it was open problem. Finally, it was solved by two undergraduate students from IIT Kanpur, while doing their summer research internship with Professor Maninder Agrawal. Okay, so Neeraj Kayal and Nitin Saxena, and so that became a very famous paper in 2002. So in fact, I also received a copy because I was in that network anyway. So when they discovered it and become a very celebrated paper, so finding a prime in polynomial time. Okay, so this is something interesting problem. And obviously after that there was a special conference in US in the honor of these people, and then they went to different places. I think one of them finished PhD from Princeton, and now he's back to India at IIT Kanpur, and another one is right now in Microsoft Research, actually working there. So anyway, so it's interesting stories that as an Indian people we have contributed to this algorithm. So that's why I believe on you young people, right? You can also do great things, and that's why I'm telling you all the important problems. So maybe you can also think about it, right? Essentially, this factorization of this actually the primality testing algorithm is based on a very nice algebraic identity. So so this algebra is very important. One simple idea that led to the development of this algorithm. So the question is, if you really want to work in the area of cryptography and you want to be really important person in cryptography, so implementation and those kind of things are anyway there, which is normal thing. But developing an algorithm or fast algorithm, okay, you can reduce the complexity of the algorithm is very, very important. So whatever you have left in your design and analysis of algorithm course, right? So you need to take a step further and look at the complexity problems for primality testing. Although this algorithm is given by Neeraj, Nitin Saxena, Neeraj Kayal, and Maninder Agrawal. Uh, Although it is polynomial time algorithm, but actually still it is not very feasible in terms of implementation. But anyway, there are like, for example, people are still using old traditions of randomized algorithm. Okay, so they may factor or they may not factor, right? I mean, they may give you a prime in terms of when you checking the probability testing, or sometimes they give you incorrect answer also, right? So those approaches are quite useful. So so I have to actually essentially describe you some of those algorithms, okay, how they work, and as you know, uh, so some of these algorithms are based on what is known as uh, Legendre symbol. So I am going to talk about Legendre symbol today. And before that, I need to talk about something really beautiful, which is quadratic residues. Okay, so I think I have given you that in discrete. I'm not sure which batch I taught what. I'm not sure, right? So I'm not sure whether I covered it in your section. Maybe your juniors have covered it. So quadratic residues are very, very beautiful thing, right? As it is said that mathematics is the queen of science, and the crown of the queen is number theory. Okay, and quadratic residues are gem on the crown. Such a beautiful thing, very powerful thing, and lot of applications, right from communications to cryptography, so security, all variety. So that's if there is a beautiful piece of mathematics, you'll find wide variety of applications, right? So I'll tell you basically, what is the definition of quadratic residues, how do we calculate them, and then based on that, we'll tell you about the Legendre symbol, why this is useful, and essentially, so I mean, today I'm not going to describe the complexity about these problems, but I will actually give you the basic definitions and some calculations, some examples, how do we compute these things normally. And then maybe in the next class, I'm going to talk about the complexity of these problems. So what are the complexity? Because that is the ultimate thing when you want to implement it, right? What is the best possible algorithm? And this is something is always very, very important. And I'm sure that some of you, I'm always positive about people, might have read about Art of Computer Programming, Donald Knuth, right? So you have not read it or you have not bought the book, you are still missing the computer science education, right? That book you should have on your table. Because see, no matter which industry you go or which area you go, if you are going to use computer science, always it boils down to implementation, right? And the implementation essentially it boils down to algorithm. For a particular task, which there could be multiple algorithms. Someone is best, someone is worst. Which one to choose, how to choose? That information is very, very important, right? So that's why I would say that you should have this book. If you have not read it, you should read it. And as I mentioned that people who have read this book, they become tech leaders, right? Those who don't read this, they do competitive programming, they become workers. So there is a difference between workers and tech leaders, right? So its choice is yours. Anyway, so let me describe this quadratic residue business. Quadratic residues. Suppose P is an odd prime. Okay. So we say that a number A is quadratic residue mod P if A is not equal to 0 mod P and the equation y square is congruent to A mod P has a solution y in ZP. Otherwise, A is quadratic non-residue. Right? So P is an odd prime. So integer A is said to be quadratic residue mod P. If, of course, A is not 0, right? Okay. The equation y, so basically A can be written as y square, right? So you can find some y in ZP such that A can be written as y square. So I'm saying that if the equation y square is congruent to A mod P has a solution y, right? If this kind of solution is there, then we say that A is quadratic residue mod P. If such solution is not there, then we say that A is quadratic non-residue mod P. So let me give you some examples. Okay. Let us take the example of integer modulo 11. Okay. So P is our 11 actually. P is 11. So what is the value of 1 square? 1 mod 11. 2 square? 4. 3 square, 9. 4 square, 16 modulo 11 is how much? 5. 5 square, 3. Is it 3 or what? Correct? Please check. I am not doing, I am just writing from this, I am not doing the calculations, but anyway. What about 6 square? 3. 7 square, 5. 8 square, 9. And 9 square, 4. And 10 square. Now you can see that when we fixed P, here P is equal to 11. So we have how many numbers? 1, 2, 3 up to 10, right? Of course, 0 is the 0 I can leave. So the non-zero things are from 1 to 11. Half of them are quadratic residues. So what numbers we are getting? 1, 4, 5, 3. So 1, 3, 4, 5, right? So there should be 5, right? Total number of 5. So there is 1, 4, 9, 5, 3. So total 5 numbers coming, right? So half of them are quadratic residues, rest of them are quadratic non-residues. Okay. So half of them are, so basically these numbers are quadratic residues. So I can write it like this. Quadratic residues 1, 3, 4, 5, 9. Quadratic non-residues 2, 6, 7, 8, and 10. So normally from 1 to P minus 1, half of them are quadratic residues, half of them are quadratic non-residues. This is just observation when you do a lot of other calculations. For example, in integer modulo 5, if P is equal to 5, what will be the quadratic residues? P is equal to 5, what will be the quadratic residues? 1 and 4, right? And 2 and 3 are quadratic non-residues. I mean, I like these quadratic residues very much because, they are beautiful. And if you want to create some beautiful thing, you have to use beautiful thing, right? So you take one beautiful thing and create some other beautiful thing. For example, a lot of such things are there in cryptography as well as in communication, as I mentioned. So one of the very popular construction is a Gole code construction. So Gole code construction is through quadratic residues. So basically, you take a matrix and so identity matrix and there is another matrix, and you try to fill wherever there is a quadratic residue, place 1 on the top in the first row, otherwise place 0 and take the cyclic shift. You get beautiful code. Okay. So those kind of things are there. Beautiful means, this Gole code has a lot of symmetries. Okay. So it's really nice. Okay. So the question is there any criteria through which I can decide whether something is quadratic residue or not? There is Euler has given one result which I am going to mention now. Euler's criteria. What it says that if P is an odd prime, then A is quadratic residues. I'm still having difficulty in writing these things, Mod P, if and only if A raised to power P minus 1 by 2 is congruent to 1 mod P. So A is a quadratic residues. By the way, you can also do some sort of operations. So, for example, let me show you. There is some sort of arithmetic which is sometimes useful. I'm not going to prove anything, neither I'm going to state the results, but I'll tell you some observations. For example, if you take this quadratic residue set, 3n If you take 3 and 4, 3 is quadratic residue, 4 is quadratic residue. You multiply them. Modulo 11, what you are getting? 1. Again quadratic residue, right? So these kind of many properties with addition and multiplication people have studied, right? So it's a good tea time problem is try to find out these properties on yours. See, when you do something, you feel the beauty, right? Otherwise you cannot, right? So you do, action is very important, right? So just do some, try to see if you can find out some properties with respect to addition and multiplication. So if you take quadratic non-residue, for example, 2 into 6, product of two quadratic non-residue is 2 into 6 is what? 12. You get quadratic residues. So, so I am just saying that play with few examples. Say P is equal to 5, 7, 11, 13. Observe. You see, you should know how to observe the beauty, right? Observe it and try to find out these relationship. It's an interesting thing. If you want to know more about these properties, there is a very famous book by Gauss book, on number theory, which is available on, obviously you can find somewhere on the internet, especially in the archive, because it's an old classic book. Okay. So where some of these properties are there. So first time, whenever you are encountered with quadratic residues, I say that you just play with it, play with its beauty, so that you can appreciate the beauty. Okay. So very interesting properties are there, and there are some unknown problems as well about quadratics. There is something which is still unknown. Okay. So that's something really interesting thing. Okay. So so let me try to establish this result that A is quadratic residue mod P if and only if A raised power P minus 1 by 2 is congruent to 1 mod P. So I'll try to prove it for you. Suppose A is quadratic residue. Suppose A is quadratic residue. So the topmost statement is given to us. That means I can say that A can be written as y square like this mod P for some y in ZP, right? We can do that by the definition, right? Now we know that if P is a prime, do you know what is A raised power P minus 1 congruent to 1 mod P? A very popular result. I think by now you might have, right, remember this popular result. So if P is a prime, then A raised power P minus 1 is congruent to 1 mod P. Okay. For any A to be non-zero, then we just look at A raised power P minus 1 by 2. This value will be, I can substitute this value, y square raised to power P minus 1 by 2, which is nothing but y raised to power P minus 1 mod P. Everywhere there is a mod P. And since y is in ZP, this value is 1. Right. So if A is quadratic residue, this property holds that A raised to power P minus 1 by 2 is congruent to 1 mod P. Okay. So one portion is easy. What about the other portion? So I normally don't, I love not doing everything. Just try the opposite side, think, okay. This was easy part, by the way. So I always do easy part. And now you see if you can do the opposite part. So opposite part, you have to assume that A raised to power P minus 1 by 2 is congruent to 1 mod P. This is given to you. And you have to show that A can be written as y square for some y in ZP. Okay. Think about it. Proof is anyway given in the book. But if you close the book and just try to, think about it, you will enjoy, right? So this is the interesting thing. So it's the characterization which is very, very important. And we are going to use it later on. Okay, so now I think By the way, I should mention that as I talked about, when you think about this proof, you have to use the idea of primitive element. Primitive element is an element in ZP for which order is P minus 1, right? Full order. Something like that. You know, I'm just giving you a hint. Think about it, how that can be used, okay? Okay, so now I'm going to tell you another very interesting thing which is known as Legendre symbol. By the way, I think some of my detailed lectures are there on these topics in another course, computational number theory, which I think I have posted only 5 lectures, but I can post all the other one, which is very useful for cryptography. Okay, so there we talked more about these things. Anyway, so assume again, P is an odd prime. Legendre symbol A by P is defined as 0 if A is congruent to 0 mod P, 1 if A is quadratic residue mod P, minus 1 if A is quadratic non-residue. Okay, so this is the kind of, you know, characteristic function. So basically, you know, if there are a bunch of numbers, I can say that, okay, if this is quadratic residue, I will put 1. If it is quadratic non-residue, I will put minus 1. Otherwise, it is 0, right? So 0 if A is equal to 0, because in that case, 0 is equal to 0, right? So this is the characteristic function, Legendre symbol A by P. So I'll actually, you know, people have found formulas. How do we do calculate these things? Let me first give you certain properties, and maybe a small example first. So first of all, I think one theorem I would like to mention about this, because how will you compute this? So this, of course, P is an odd prime. This Legendre symbol is same thing as A raised to power P minus 1 by 2 mod P. So you just saw that A raised to power P minus 1 by 2 is the characterization for the quadratic residue. So basically, you know, these two things are kind of equivalent, right? So let me show you how. So the proof is really simple here. So I am going to do it. So if A is a multiple of P, suppose A is 0 mod P, right? It's multiple of P. Then we know that A raised to power P minus 1 by 2 will be 0 mod P. Trivial, right? So if A is, so both sides will coincide, right? Now if A is quadratic non-residue mod P, then we know that A raised to power P minus 1 by 2 will be congruent to minus 1 mod P, right? Since A raised to power P minus 1 by 2 whole square will be A raised to power P minus 1, which is something as 1 mod P, right? Similarly, if A is quadratic residue mod P, we know that if and only if A raised to power P minus 1 by 2 is congruent to 1, so which is matching on both sides, right? So essentially, you have this formula. Okay, so when we want to compute this Legendre symbol, I can look at this expression raised to power P minus 1 by 2 mod P, and so we need to develop the algorithms. How do we compute these things? Okay. Anyway, so let me now show you some examples before we proceed further. And another very important thing, as you know, any number, there is a fundamental theorem of arithmetic, you know, remember, no? If n is an integer, we know that n can be written as partial product pi e raised ei, I is equal to 1 to k. Fundamental theorem of arithmetic, right? Any integer n greater than 1 can be written as product of prime factors, right? So p1 raised to power alpha 1. So e1 here, p2 raised to power e2, and so on. pk raised to power ek. So for example, 15 is equal to 5 into 3, product of two prime numbers. 16 is equal to 2 raised to power 4. 18 is equal to 3 square into 2. So 3 square into 2 raised to power 1, right? So product of prime factors, any integer can be written, right? So this is the fundamental theorem of arithmetic. Okay, so another symbol, okay, it is known as Jacobi symbol. It's kind of generalization here. Is partial product I is equal to 1 to k a pi raised to power ei. So remember, on this side, right hand side, it is Legendre symbol, because here in kind of denominator you see prime is there, right? Whereas here n is an integer. Okay, so Jacobi symbol is generalization. In the denominator there is a general integer n. Then we compute these things, it becomes Jacobi symbol. Essentially, it is defined like this. For each, you write down n is equal to partial product, right? And then you compute for each one, right? Okay. So for these factors, so let me calculate it for you as an example. What is the value of 62789975? Jacobi symbol. Okay. So since 9975 denominator can be written as 3 into 5 square into 7 into 19. So we have this value is 6278 divided by 3. It's actually not division, but I'm just writing it like this. So anyway, 6278 by 5 whole square into 6278 by 7 into 6278 by 19. Now, how do we compute these things? I will tell you in a minute, but here I am just writing it. It is 2 by 3 times 3 by 5 whole square, 6 by 7, 8 by 19. And then this is minus 1 whole square, minus 1. Overall value is minus 1. So these expressions are Legendre symbols, okay, and this is a Jacobi symbol, because here there is an integer and here there are prime numbers in the denominator kind of thing, right? So this is the formula. And how do we compute from here to here? I'm going to show you some more properties, but at least this is how you do, okay, in general. If I want to compute Jacobi symbol, I just expand it, write down n as a partial product of, the product of prime numbers, and then expand this calculation, right? So the question is, how do we compute these quantities, the Legendre symbol? So as you know, 6278 by 3. So, here actually you can use this formula, right? This formula you can use a raised to power p minus 1 by 2 in each case, right? But I think there are some shortcuts for doing couple of things. Let me show you. Especially for Jacobi symbol, there are certain properties which I would like to share with you, okay? Properties of Jacobi symbol. Number 1, if n is a positive odd integer and m1 is congruent to m2 mod n. So m1 is congruent to m2 mod n, then Jacobi symbol M1 by N is same thing as Jacobi symbol M2 by N. So I think, of course, it requires proof. I mean, I'm not going to do any proof, but you can enjoy. I mean, try to prove and see. Too much work, right? Yeah, but whatever you can do, you can do. Right? It's a but trial is important actually, right? So because see, otherwise, there's so much material on Jacobi symbol, you can keep on talking about it anyway. So the result is M1 is congruent to M2 mod N, then this happens, okay? Second property, if N is a positive odd integer, same N as a positive odd integer, then 2 by N is equal to 1 if N is congruent to plus minus 1 mod 8 and minus 1 if N is congruent to plus minus 3 mod 8. Another interesting property, so if in the numerator it is 2, then we have this result. Third result, again N is a odd, we are assuming again N is a positive odd integer. M1 M2 by N is equal to M1 by N times M2 by N as a Jacobi symbol, right? In particular, if N is something like 2 raised power k, 2 raised power k into t, and t is odd. By the way, if you're not able to prove all of them, it's okay. I mean, there is no harm because, the first introductory course, even if you know the properties, that is okay. Then m by n is equal to 2 by n raised to power k times t by n. Okay, so this is another property. As a product, if n is equal to actually 2 raised to power k times t, where t is odd, then Jacobi symbol m by n is Jacobi symbol 2 by n raised to power k times Jacobi symbol t by n. And I think last one is an important one, the fourth one. So fourth one, so this time m and n are positive odd integers. This is a condition. M by n is equal to minus n by n if m is equal to n congruent to 3 mod 4. And this is n by m otherwise. This is very useful property. You will see that, you can switch the role of m and n here actually, right? So m by n becomes n by m, positive or negative, depending upon what is the relationship. Okay. So I think now I am ready to give you an example actually. Compute 7411 by 9283 Jacobi symbol. So if I want to use property 4, can anyone tell me in the class what will be the value of this? This property 4 I am going to use. Will this be a case first or the second case? So if both m is congruent to n is congruent to 3 mod 4, which one should be there? So you need to check that condition, accordingly decide, right? So of course, I can write it down. By this property 4, this becomes minus of 9283 divided by 7411. So basically, note that. So normally whenever the denominator is high, we apply property 4 and switch according to the case. Okay. So in this case, we are switching and this value is -1, minus times of this because of first condition is applied. Okay. Now, what is property 1? This is by property 4. Okay. Now, if you look at property 1, if M1 is congruent to M2 mod n, then M1 by n is same thing as M2 by n. So, using this property 1, this value will be minus of 1872 divided by 7411. Okay. Now, I am going to factorize the numerator, right? And I can actually compute using property 3. This value will be minus 2 by 7411 raised to power 4 times 117 divided by 7411 by property 3. Okay. So what happens to this? You can actually see by property 2 what happens actually, right? You can simplify this by property 2. So we are finally getting something like negative of 117 divided by 7411. So we are getting this whole value as negative of 117 divided by 7411, right? By property 2. Okay. Then this is nothing but minus of 7411 divided by 117 again by property 4. I have switched the role. This is equal to again minus 40 times 117 by property 4 again. Sorry, by property 1. Yeah. And this is nothing but minus 2 by 117 cube times 5 by 117 by property 3 is equal to 5 by 117. This portion will go to 1 by property 2, which is same thing as 117 by 5 by property 4. This whole thing will become 2 by 5 by property 1. This is minus 1 by property 2. So overall value is minus 1. Now you can see the how much tedious calculation, right? The question is there an efficient algorithm? How do you compute these things? So that I'm going to talk about in the next class. Essentially, also I'm going to talk about the complexity. What is the complexity of computing Jacobi symbol and the Legendre symbol, right? That is an important aspect. Okay. So what I did today, only introduction of the quadratic residues, Legendre symbol, Jacobi symbol, right? And some of these properties. Obviously, nobody proves it in the undergraduate, at the first class of cryptography, but if you are doing computational number theory, probably we can go in proving some of these properties. But here is just one, item song kind of thing, right? So that's okay. Anyway, so I think thanks. So let us meet. So by the way, any question about your project? Everything is fine. So some people are saying that they have changed their mind and they want to go for exam. So it's always problem. So again, I always say that it's जैसी जिसकी श्रद्धा. अगर आप प्रोजेक्ट सबमिट नहीं करोगे तो बाय डिफॉल्ट आप एग्जाम तो दोगे ही दोगे, नहीं जाओगे कहाँ, राइट? So that option is anyway there, right? So I'm not going to make any changes in the list, whatever, because it takes a lot of efforts and time to keep on changing the list. Those who have submitted for the project will go ahead. If you don't want to do the project, you can always go for the exams, right? So, and those who are doing projects and still want to give exam, I have no problem, right? Okay, so fine.